What's up, everyone? It's really good to be back, and it's been a while since I've made a video. I've had a lot going on in my life. Started a new job, bought a house, moved my office, so lots going on. But I'm back, and I recently put out a LinkedIn poll on, what would be the next subject that some people would like to see, and overwhelmingly it was between my most common Go-isms and applied concurrency. It ended up being applied concurrency, which is a really interesting subject within Go, because that's pretty much the entire reason that we use Go, is that it is a language that makes concurrency, parallelism plus, as I like to refer to it, very, very easy. So it's a very interesting topic. So first things first, let's do a really pretty simple closure, right? So with a closure, it's just basically an inline function that returns all on the same line. So yeah, let's do it. Okay, first thing we're going to do is import sync. This is a library that does a lot of synchronous operations. So you'll use it a lot with concurrency. So now let's establish a wait group. So what's a wait group, right? So this is going to kind of get into how Go actually deals with asynchronous operations of some kind. So it's not like Java, where if you create an actual thread, like it actually takes up a physical thread of the machine. Essentially the way that it goes is that the compiler basically just generates a bunch of subprocesses on your machine. Right, that's pretty much it, and it sort of hands off the operation and multi-threadedness or whatever to the CPU to deal with. And so if it's just spawning a bunch of sub-processes, that actually makes for some very interesting behavior that we can harness, right? So the issue, though, becomes if I'm just going and spawning subprocesses, how do I know that I'm supposed to wait until those subprocesses are done executing before I move on and do something else? Well, that's a wait group. So we're going to say, you know what? I'm going to go for 10 rounds of functions. So we're going to call it rounds. Rounds. I'm getting used to this baller new Kinesis keyboard that I just bought. I have a review coming up on that in like a month. So let's just say that we go for 10 rounds. We have a sync wait group. Did I spell that right? I didn't spell that right. So we're going to add something. We're going to add the number of rounds that we're going to that wait group. And what we're telling the system is that, hey, I expect you to complete 10 Go routines, right, from this wait group. If we look at the doc, what does it take? Right, all it takes is a delta. It just takes an integer of some kind. That's all it takes. If you look at the very, very top line right here, right? So it just takes some kind of integer. So we're just telling the system that, hey, within this wait group, we're expected to have 10 Go routines. And once those 10 Go routines complete, then our wait group is done waiting and done blocking, and we can continue with execution, which is, nice. So just do a really simple like for loop here. And 0. Yeah, this keyboard's kind of a pain in the ass to get used to, but that's okay. Rounds, and then we're gonna do I plus plus, and then we're gonna say that critical word right there, that go func. So any function that we want to run as a Go routine, just put the Go in front of it. Now, just because you put the Go in front of it doesn't mean it's automatically going to work or the tooling's going to work as you expect, and that's part of the reason why I'm making this video. When people just say, well, just add the word Go in front of your function. Well, yeah, but there's also a lot of other stuff that you really need to focus on if you're going to do that. So this is just a very simple closure. So what's a closure? Again, just basically an inline function that returns. And let's call this the function print me. And it's going to take our ri and the address of our wait group, right? And then we're also going to pass it in I. So that's just, standard closure syntax. So now we're going to do a function called print me, right? And that's going to, well, what are we passing it? We're passing an I, which is an integer, and then a pointer to a sync wait group, right? And the first thing that we need to do within this function is defer, and this is why we pass the wait group. We need to defer it being done. So what was that saying? Remember, when we have a wait group that's waiting for a certain number of goroutines to be executed. It's just sitting there waiting and counting. Well, how does it know that of that wait group a function is done? How does it know that? You would call waitGroup.done, and that's why we pass it by pointers, because we want that specific wait group. Now, what's great about this is you can create multiple wait groups. You can have wait group 1, wait group 2, wait group 3, and as long as you're passing that certain wait group to whatever function you want to run, right? And you're saying, hey, defer until the wait group is done, which basically says, hey, at the very end of this function, we're done. Whatever is after the very last execution done within this function, okay, now you can call wait group done. And then the wait group knows that, oh, okay, a function assigned to a goroutine assigned to my wait group has completed. And then we're just going to do an FMT, one of my favorite and most handy things I've ever used, which is the printf. We're just going to say I'm go routine, and we're going to say let's give it a digit and a new line, and then we're just going to pass it I. So, okay, now we've done all of that, but we also have to say to the wait group, hey, this is where you're actually going to, we're going to wait until all of our goroutines are completed, and then you can, at this point, okay, we're done, and then we can move on with the execution of our program. That's waitGroup.wait. Again, because this is just going out there and spawning sub-processes. It's not aware of what those sub-processes are doing, nor when they're going to be completed. We have to tell the program to track those for us. And, unfortunately, one of the things with this is that it's not terribly intelligent about it, right? We're just adding an integer. But by passing the reference to that wait group, we are able to keep track of which goroutines are running where for the most part. It's not my favorite way of doing things. I think they probably could have written this better, but it does work for what it is. So this is the most basic version of doing goroutines. It's a very simple closure, and look at that. Now again, goroutines, are just spawn sub-processes. That's it. So the order in which they are spawned is something that is not of concern. And order of, if you're trying to do things in a specific order, goroutines are not what you should be using. They're not at all. It should just be, hey, I have to do the same thing a whole bunch of times, and I don't care. They're not dependent of each other. So, let's think about this behavior for a second, though. So we're just spawning sub-processes, right? Well, then what if I say here I want to do, instead of rounds, I say I want 20, right? So at this point, remember, we've told our wait group, hey, wait for 10 of these go routines assigned here to be completed. Wait until waitgroup.done has been called 10 times, right? But we're doing 20 go functions. We're responding 20 go functions, right? So someone's walking above me. What does that look like? Well, what happens? So you can see here, that's not 20 go routines, right? So what happened here is that all of these go routines are still being spawned, spawned and spawned and spawned and spawned, right? But our wait group has only been tasked with tracking 10 of them, with waiting until 10 calls to waitgroup.done. So essentially, this is the number of times you can print via a go routine. This is the maximum number of times that it got done. So you can see here, 1 would have been called technically before 5 or 18 or whatever, right? But because it did not get to waitgroup.done first before these 10 functions did, right, it doesn't get printed. It doesn't happen. So that's it's very funky, but again, just think of it as it's not going out there and physically taking threads on your machine, going out there and taking, and then putting data here and putting data here. No, it passes all the subroutine and sub processes off and just says, here, I'm just gonna sit here and wait, and whatever gets done, right? The program itself is really not aware of how that is happening. It's just kind of doing its best to track these things. And you can get fairly more granular with tracking them if you want to. It gets really complex, really quick. But let's do now a sort of more complicated example. Now we've got our nice blank space. A fairly common thing that I run into with Go, at least within my job, like a fairly common scenario that's very illustrative of some of the finer points of how concurrency works, is concurrent database calls, because I have to assemble from multiple calls a single data structure, right? So if I'm well, first off, put my money where my mouth is, and let's do a thing struct, right? So, and again, you'll see this all over the place within Go. It's very, very common. So we'll have some kind of data structure. For this, I'm going to generate a bunch of UUIDs. We just do that because I want to have a function that both returns an object and an error, because we're going to do some interesting stuff with buffered channels. Very, very interesting stuff. So we're going to call this UUIDs. And it's just going to be string, right? And we're going to do some really fun stuff with JSON later. So let's put that in here. We'll just call it UUIDs. And then we're going to have a mutex. So what's a sync.Mutex? For those who have not taken college level computer science, a sync.Mutex is essentially a way to share memory between concurrent processes. And what a sync.Mutex will do is essentially lock that memory for a given operation and then unlock it. And that ensures memory safety, because you cannot share memory in Go, and that's part of the design paradigm in order to get rid of problems around pointers and such things. And it works really, really well. So just think of it as a lock. That's basically what it is. Cool. So we've done that. Now let's do some kind of function, some kind of generation function. So the first thing that we're going to do is we're going to make a new thing, which returns a pointer to that thing. Okay. And let's just say we want to create 1,000 of them. So let's just say L is equal to 1,000. Well, now we need to make a channel. So what's a channel? Right? I like to think of a channel is it's kind of like this wire. This is Cat6 Ethernet cable. And a channel is just this thing that can, on one end is the function execution, right? And on the other end is the go routine. And however the go routines end up constructing each other and all these other kind of things, you essentially have, you know, a whole bunch of these wires. You have one wire connected from the function execution to each go routine. And that's kind of how you think of a channel. So it's a way to pass information via the two things and do it in a memory safe manner. So how do we create a channel? Specifically, how do we make a buffered channel? What's a buffered channel? Well, I'll show you first. We're going to call it errors because we want to track errors using it. Again, very, very common thing I do in Go all the time. And so here we have said, make me a channel that has a specific type. And because channels have types, you can't just pass any information you want willy-nilly. You could technically just use it to pass byte slices. That's also a very common thing, but that's a far more advanced topic. And it's kind of Go's way of dealing with generics in kind of a fun way. But here I'm just going to be passing errors back. Technically, I could create a channel that takes a thing, one of those thing structures. So it has a channel of errors, and it can handle a buffer, right? It has a buffer, so it creates a certain amount of memory available to be used, and that buffer is size of 1,000. That's it. So remember, so we're making that wire between the function execution, wherever we're executing the function, adding that little fun go keyword in front of our function and running it a whole bunch of times. And that's that wire that plugs up into that go routine. Here we also need to do a wait group. WG. New sync. Wait group. For the same reasons that we talked about earlier, we're expecting a certain number of go routines to be done. Right? Look at it. Right up top. A go routine waits for a collection of go routines to finish. I love Vimgo. Vimgo's so good. I love that. Because you can go to anything. As long as you're hovering over it, you can say go doc. And it'll tell you what that thing is. I love that. Very cool. Now we need to add the number of go routines that we're going to run. Add that to that wait group. And then, you know, it's another for loop. Formats everything for you too nicely. I love Vimgo. It's so good. So, okay. Well, what's the function that we're going to add here? Well, let's call it, I don't know, gen. We'll just call it gen, like generation, right? Because we're generating a bunch of UUIDs using it. Here we're going to be using a pointer receiver. So, okay, so we're going to have a pointer receiver here. It's going to be a pointer to a thing, right? And we're going to call it gen. And what's gen going to take? Well, it should probably take that wait group, and it should probably take that channel, right? Because it's a go routine. And we want it to not only call waitGroup.done, but we also want to grab some data from that go routine and pass it back to our main execution. Okay. Well, then yeah, that's just what we should pass. So let's pass a sync dot wait group, and we're also going to give it that channel. No need to put an error on it or a pointer on it. Their pointer's natural. I'm not going to explain it, but it's technically not it is a pointer, but like it's not. They're always pointers, all right? That's why you don't need to reference it as a pointer, because it is a pointer. Anyway. We call our defer. So don't do this thing until everything is done. And we've reached our closing bracket. We've gotten to the bottom of this frame of the stack. Cool. Okay, so if we want to generate a UUID... what's a good way to do it? We can just use mathrand to do it. I mean, we could also use Google's UUID. In fact, let's do that. So let's do go go import github.com Google. Cool. So we want to generate a new UID. So we call this UID is equal to UID dot new random, right? Because that returns a UID object and returns an error, and that's something we want just for the contrived question of how do we pass errors, right? How do we pass data back from a go routine? Well, we pass it via a channel. Oh, look, we created an error channel. Let's go pass things up there, right? Okay, so this needs to be error. Cool. Okay, so we've created our UID, we've created our error. Well, now we need to do something with them. So let me do this again. There we go. There we go. I don't know why. Sometimes the compiler just gets like stuck with some of the auto-completion stuff. If you don't do brackets the right way, it gets really weird. Okay, so we've done that. So now we need to check if our error is not nil, right? So if error is not equal to nil, then we're gonna do something really interesting here. We're gonna have some interesting syntax. We have our, we're gonna place it on there. And we're gonna return. Just end it. So we're saying if the memory is allocated and something is assigned, so if it's not nil, toss it onto that channel, right? So that channel is sitting there listening, right? Because we created a buffer channel, and that buffer channel is sitting there saying, hey, I've got 1,000 mail slots for 1,000 pieces of mail. That's our error. And I'm waiting, I'm listening on the phone. I've got a big loudspeaker, and I'm waiting to hear an error from somewhere, right? So if it is, return it. If everything's gone well, we haven't gotten an error. Well, now we want to append it to this guy. Right? So we want to start appending to that slice of strings. So what do we have to do? Well, we would say tmute lock. We call t.mute.lock, and all that really does is just say, hey, this data structure that we've instantiated, lock it down for a moment with this particular go routine. So nothing else can interfere with it. Nothing else can call it. So essentially what's going to happen is whatever is the quickest executing go function is pretty much going to be in like the first parts of the array at the lowest numbered addresses. And the slower the go routine, the further up the slice it's going to be. Because it just takes whatever happens first. Whatever first calls waitgroup.done is what gets done. Right? First. So then we're going to say t.uids is equal to append. And we're going to come in here and we're going to append t.uids and fmt.sprintf, perhaps the greatest single print function that has ever been created. And we're going to say %d, %s, excuse me. And then we're going to say UID. And then we're going to unlock it. Oop. Cool. So this is something that I really want you to understand that's really, really super key. Notice that I didn't lock the data structure before I had generated the UID. The point of using goroutines is to get the execution of your program done as fast as possible, which means minimizing the number of things that are happening while your data structure is locked. So literally the only time that I lock or unlock a data structure is when I know that what data I need is there to be readily appended to that data structure. And then the only operation that I perform is that append. Again, it's a very, very common design paradigm within Go. So now we just need to write our function. We call it go t.gen, and it takes a wait group, and it takes a channel. Not bad. Really all that's left to deal with at this point is the buffered channel, and to check and see if there's any errors, because if there's any errors, we certainly want to have that logged, handled in some way. Someone needs to be notified if there's database errors, right? That's not good. So here's the cool thing about a buffered channel. Just because it's buffered to 1,000 does not mean that its length is 1,000. So I can sit here and say, okay, if nothing gets passed from our Go routines, if nothing gets passed onto that channel, right, then that channel's length is going to be 0. Again, this is a very common design paradigm. So we say if the length of C, if anything is on that, if anything is contained within that channel, right, is greater than 0, then do something, right? So fmt dot print line, or excuse me. I'm all discombobulated today. So, if the length of C is greater than 0, that means that there's been an error that's been dumped onto our channel. We need to check that. So for error in the range C then we're going to say fmt dot print line. We're going to print the error. Again, very common. You would log those, whatever those errors happen to be. And here's a way to do all of that completely concurrently. So let's iterate through this again, right? So we create a new thing, structure. And we're saying we want to generate 1,000 UUIDs. First thing that we do is we make a channel, a buffered channel, in fact, with our declared type, which is error, and the length at which that we want to have buffered. L, in this case 1,000. Then we create a new wait group to ensure that all of that happens. We also create our wait group.wait. Let's check and see exactly how fast it is. So I'm going to test this as a function. So here I am going to sit and say, you know what, let's call this runner. Here's going to be your first performance test in Go, right? So we're going to exit out of here and looking at less. So I'm going to say v main test.go. So package main. I'm going to import Go import testing. I'm going to say func benchmark runner. We're going to test that we're going to pass it the testing B for benchmark testing.b. B is a type passed to benchmark functions to manage benchmark timing and to specify the number of iterations to run. Isn't that nice? And then we're just going to say runner. Was that? We just call it runner, right? Yeah. Then we say go test bench. And hey, look at that. So we did a whole bunch of runs, 1,000,000 runs from the look of it, and it only took 0.00412 nanoseconds. That's really fast. That's crazy fast. So that's really it. That's a very basic way of doing a whole bunch of Go routines that pass things over a buffered channel and all run concurrently. So that's going to be it for probably this video. Those are two things to really kind of get you started, get you running in the right direction. And then my next video, I'm going to do like an API around it, which also does some interesting things around concurrency, including unbuffered channels. And we're also have a video planned where we kind of go down this really interesting rabbit hole with some of the UUID generation, which package you should use, why is rand not really all that random. Pretty interesting stuff, so stay tuned.